Welcome to the last segment in our first week lecture. So in this segment, we'll talk about the software stack. So we said that we will map each layer in the software stack to exactly where it runs and how it can be optimized. So from the perspective of OS, operating systems, drivers and runtime layers, we will see exactly what are the layers that are individually contributing to this entire deployment of AI workloads and how we can optimize them. So the layered software architecture that connects your Python code to the silicon and transistors, which is actually running your code, we will see how to map them, and 5 things we will cover. So first we will see the full AI software stack from user space frameworks to kernel drivers, from where exactly we write the program till the kernel drivers, and then basically how it maps to the hardware. So far we have seen the hardware, right? We have seen the CPUs, GPUs, we have seen the accelerators. So exactly what are the systems, hardware systems that are running the AI workloads and how they accelerate, what are the performance metrics that are involved, all those things we have looked at. But now we are focusing on exactly on the software side. So we will declare the different kernels or different components of CUDA framework like CUDA Runtime, cuDNN, cuBLAS, NCCL. So different libraries are there in the NVIDIA software stack. Because most of the AI workloads will be offloaded to the GPUs for both AI training as well as the AI inference, we will look at various components of the NVIDIA stack also. We will see the GPU driver management, kernel modules, as well as the different CUDA versions compatibility, because what exactly breaks the chain or runtime, that also we will see. We will understand the containers runtimes. So we will have a dedicated week lecture for the containers and deployment through containers for the AI workloads. Here we will introduce you to the containers and basically the runtime, and then we will identify key kernel in the operating system, which is Linux, and what exactly the configurations that we should follow to extract the most out of the system for the AI workload deployment. Here is the entire software stack layer by layer you are seeing. In the top, obviously we will write the applications. So here your user applications line. Applications means the code that we are running, maybe transformer codes or PyTorch Lightning, Keras, whatever we are writing through different APIs, also they will be connected. So here your application code will run, and then in the bottom you have exactly the ML framework. ML frameworks are usually defined by libraries or packages from PyTorch, TensorFlow, Zax or Flax. So these are the ML workloads defining packages or workloads that we will see. So essentially the codes that we are writing, that will be based on these ML workloads which are defining the machine learning flow, the forward pass, backward pass in PyTorch, TensorFlow and so on and so forth. When we write these programs or when we write these frameworks using PyTorch, let's say, they will be compiled, and let's say this torch.compile will actually compile these workloads and generate the computation graph. Okay, so here all your optimizations, graph optimizations will happen also, because essentially your AI workload or AI workflow is nothing but a computational graph, because the computational graph where these inputs are going through or traversing through several stages of computation, that will define this computational graph, and that will be extracted from your PyTorch definition, and that will be compiled through this torch.compile, or let's say XLA if you are writing in TensorFlow, TensorRT, TVM. So different frameworks are there to compile the ML workflow that you have defined in PyTorch or TensorFlow, so different frameworks. Here the optimizations also will happen, because some operations will be fused, some operations will be simplified, some operations will be also eradicated if they are not useful in the workflow. That will be analyzed by this compilation flow, and that will be optimized here in this stage. And then the middleware libraries will come into picture, because these libraries have definitions for the, so several thousands, millions of algorithms are defined in these libraries. Like cuDNN has the algorithms for your convolutional neural networks or transformer attentions. So these libraries have algorithms to execute this type of workloads. You have batch normalization, you have dropout, right? So all these different algorithms are defined in this cuDNN. cuBLAS is another library. So here you have the matrix multiplication. So different algorithms for matrix multiplications are defined here. NCCL similarly, you have the communication library. So this is where all your different communication frameworks and algorithms are defined here. cuSparse, cuFFT, so sparse is for your sparse computation. So where you have different sparse computations, the algorithms are defined in this library. FFT based algorithms are defined in cuFFT, Thirst. So different algorithms are defined in these libraries. So based on the computational graph that we have defined or the compiler has optimized, for that each operation will be mapped through different libraries, algorithms and so on and so forth, because based on the speed up or the performance that we want to get, so heuristically algorithms will be chosen at the first flow. So if we run the let's say training algorithm at the first run, your cuDNN, let's say I'm training one convolutional neural network based on a target system, let's say GPU based system, NVIDIA GPU based system that we are running on. So cuDNN will choose one algorithm heuristically based on the target, which it seems that it will run faster in this particular target, and for that it will actually run using that algorithm. Okay, so similarly, if it is general matrix multiplication, if it is sparse computation and so on and so forth, the algorithms will be chosen. So the first run will not be as fast as you expect it to be, because the algorithms are to be chosen and then the benchmarking will happen, and subsequent runs will actually gain the cached algorithms that will run faster than the previous runs. So that's how the middleware libraries are important to make the choice of which algorithm it should take, and it should run the computation graph that you have got in the compilation stage. In the next stage, we have the runtime. So runtime is highly important. Here let's say libcuda.so. So this library or this runtime will essentially do the memory management, the kernel launch, streams if there are streams, and if you want to overlap the streams and the data or the kernel launch together, so these pipelines will be also managed by this runtime. CUDA graphs also will be managed through this runtime. So this runtime is essential for managing the pipeline of the stream, the kernel launch, the memory management and so on and so forth. In the next stage, the CUDA driver APIs like libcuda.so actually does the connection or bridge between the runtime and the driver that is going to handle the hardware interface. So here the context management, context switching between different streams will be managed, and it actually is persistent across different CUDA versions. So this does not usually change because this is a very stable ABI definition. In the next stage, we have the kernel driver nvidia.ko. So this driver is the interface between the API that is being defined or called here and the hardware that is running in the bottom. So here we have the streaming multiprocessors. So in the GPU side, when we saw that the AI workloads will take the help of tensor cores or the CUDA cores based on what computation that we are trying to achieve or give, the memory where exactly these data should stay. So these will be managed by these runtime and the API, but essentially driver will hand over the control. The DMAs will be controlled by this, interrupt will be handled by this driver, and power management, the clock synchronization, the clock scaling or descaling, and the power management, everything will happen through this driver. So this driver should match the runtime that we are actually installing in the CUDA framework. So that's why they should match. If your runtime cannot communicate the driver, so essentially you are not communicating to the hardware. So the hardware, the underlying hardware, should get most out of the optimizations that compilation has done through the runtime, and runtime should match the driver's specifications, so that the matching should happen, right? So when we will talk about the containers, the different versions of the CUDA toolkit, you will see that runtime has its version matching with the toolkit that or runtime that we are installing, right? So talking about runtime, as we have seen that runtime manages the memory and execution. So like we have in our CPUs when we let's say program in C, right? We do dynamic memory allocation by malloc, calloc, and so on and so forth. Similarly, here we have CUDA malloc, the CUDA free, which allocates or releases the GPU global memory from the HBM, for an example. So if we have, let's say, our DGX machine or our hopper machines where the HBM is there, the global memory is staying inside the HBM. So what exactly the memory will be allocated, how much memory will be allocated, where from the copy will happen, so all these will be defined by this runtime. The stream management, the graph management will happen. So it captures and replaces the sequences of the graph operations from the computational graph, and with reduced launch overhead, so that it does not take much time in the communication. So all this optimization, runtime optimization, happens through this CUDA runtime. The cuDNN, as I have said, that all your algorithms pertaining to the convolution, attention, your activation, dropout, so be it recurrent neural network, multi-head attention, so whatever you are trying to run, it provides the necessary algorithms for that. And as I said, that it heuristically chooses the fastest kernel for the given tensor shapes as well as the hardware. So whatever the specifications that we are giving in the compilation stage, or let's say in the model framework, that will be taken into consideration as well as the hardware, and based on that the fastest kernel will be chosen, and then the run will happen in the first go. So similarly, we have flash attention also available in cuDNN later stages in the 8.9 plus versions for memory efficient attention. So flash attention we have mentioned in the previous one example. This is one, let's say, memory efficient version of the vanilla attention mechanism that is widely used in transformer based models as well as in the large language models. This is just an example. Similarly, when we will run the convolutional neural networks or the recurrent neural networks or any other generative AI models, you will see that the kernels that are being chosen from these cuDNN libraries. Similarly, you have cuBLAS, where you have the single precision, double precision, or half precision matrix multiply kernels that are defined. So these are the backbones of all the AI algorithms that you see nowadays. And then you have also mixed precision cuBLAS GEM-X execution through the general matrix multiplication with tensor core acceleration, where you have you want to achieve the acceleration or speed up through the mixed precision. This type of implementations are also there. Here is just an example, torch.matmul we call in the PyTorch. So essentially that ultimately calls the cuBLAS GEM routines internally from the library, and it runs the best possible way for the target hardware, right? So you know when you are writing this particular code from which library that algorithm is going to be picked. As I said, CUDA versions compatibility is required. So essentially CUDA 12 and the later versions 12.x requires driver version. This toolkit version requires driver version greater than equal to 525.85.12. This is just an example. When you will be watching these videos, and when you will be running the codes, whatever toolkit that you are running, the driver version should match. So that is the takeaway from this slide basically. Okay. From the operating system side, so we usually install the toolkit, install the driver for the CUDA. We have the target hardware, we have the operating system, we are writing the code, we are compiling the code, and essentially we are running the AI workload inside the GPUs or CPUs based on whatever resource we have available. However, we mostly, at least most of the developers, do not actually understand the operating system features that are essential for AI workloads. And that is one of the most important things when we try to run big AI workload. Okay, big AI workload, I mean in terms of the parameter size of GBs, or let's say few hundred MBs, and so on and so forth. So usually if we see the Linux kernel, right, so Linux page has the size of 4 KB, right. So this is usual standard size of 4 KB Linux page size by default settings. Okay, but usually when we have the large AI workloads where we have multiple hundreds of MBs of parameters, or even in terms of GBs, right, gigabytes of size of the model parameter size, then this page size will have lots of TLB misses. So TLB means the translation look aside buffer. So if you have gone through the operating systems, how it works, you know that this is required for the virtual memory address to physical memory address translation, right. So if we use smaller page size, which is very much fine for many workloads, however, if we have page size of, because we need to access these many GBs or hundreds of MBs of parameters as at one go, we need to have huge pages. Okay, so huge pages is one such configuration where we try to reduce the TLB misses by increasing the page size in our case. Okay, so transparent huge pages, or THP, is one such setting in our kernel, where the kernel auto promotes the pages, often enabled by the default page size, but we can increase it to 2 MB, let's say, right. So if we have 2 MB page size, then the TLB entries will look for this much of page size. So essentially our TLB misses will be less in that case, and we will get huge performance gain for our data transfer as well as the overall performance. Similarly, if you see the CPU governor for the power management, obviously we have the CPU frequency monitor, or CPU frequency performance governor, right. So we can disable, obviously by default usually these are essentially disabled, but we can enable them to make faster GPU, or let's say get the maximum clock speed in terms of AI workload deployment, we can get that. And similarly for your NUMA settings, so NUMA, non-uniform memory access part, that we have discussed in the architecture side or system side, we can disable the balancing. So we can manually pin the NUMA CTL logic for the best performance out of these CPU settings, okay, which is basically taking care of the performance of the CPUs. We have also the hierarchical resource controller, because we have CPUs, we have memories, we have input output devices access. C groups or control groups usually help us to limit the quota per pod that we are actually containerize the application for. So this part also we will see in depth when we will deploy the AI workload as containerized application in the system. Okay. Similarly, we have the IO memory management unit, right? Input output memory management unit, which translates device virtual addresses to physical addresses for DMA safety. So there are several settings which required for GPU pass through in virtualization. So if we are using virtualized GPUs, in those cases the IO input output memory management unit in pass through mode for PRR DMA will be required for this GPU direct access. Okay. So in these kind of scenarios, what are the settings that are required to access or to get most out of the system, that we are talking about here. Similarly, the driver management, we can monitor the GPU utilization through NVIDIA SMI, right? There are several commands to see the utilization, the utilization in terms of resources inside the GPUs also, like how much tensor cores that we are using, how much tensor cores are available, how much CUDA cores are available, how much functional units we are trying to achieve, or which kernels that are actually getting bottlenecked into the computation, or maybe in the which are the let's say IO operations which are getting bottlenecked by the data offloading and data onloading. So different performance monitoring we can do through different this NVIDIA SMI driver management system. And there is also DCGM, which is data center GPU manager, for your health checks, profiling, and field injection for testing also. Okay. So these are different mentions which we can take into account to see which are the resources that are left, and essentially which are the bottlenecks that are happening in this AI workload, and we can expedite the or we can accelerate the process of AI workload running in the system. So configuration checklists there are many, but importance are to set performance governor, disable C states. C states are basically the states which will say that this is the gradually we increase the clock speed. To disable that means we will enhance the clock speed and we will utilize the maximum clock speed as per the AI workload goes. Okay. We should enable the huge pages also. So in the size wise, we can define how much page size we want to allocate. So these are the different settings that we can apply. In the operating system kernel itself, we can set the GPU persistence mode to true, so that we track the performances as well as the resource management. And then the topology, we can also check what is the topology that we are using, so that we can distribute the workload accordingly. Okay. Containers are key factor because virtually mostly, if you see the production grade AI workloads in modern day organizations, mostly are running in the containers. Okay. So that's why we need to understand how these container environments actually encapsulate different libraries that are available there. Okay. So containers usually run isolatedly, right? So you have these containers, it has its own file system, its own dependencies, its own libraries, and so on and so forth, right? But operating system is basically holding or hosting the CUDA driver, right? So, or let's say your GPU driver. So how it communicates to the containers that you are deploying for your AI workloads, that are through the container toolkit. Okay, so that's why this NVIDIA container toolkit is also important when we are trying to offload or deploy the AI workloads through the containers, right? So if you see this NGC, which is the NVIDIA GPU cloud for container registry, you will see that pre-built, already optimized containers are also there, available from packages or platforms, frameworks like PyTorch, you have TensorFlow, TensorRT, Triton, and so forth. So you can go to this catalog and see actually what are the containers available, and based on your requirements you can actually take those containers. And we usually prefer these NGC containers because they are already benchmarked and includes the flash attention, the transformer engines already pre-installed within these containers from this registry. And obviously, as I said, that when we deploy the containerized AI workloads, the toolkits inject the necessary packages or libraries which are required for your access from the containers of the hardware, right? So these libraries we need to have access from the containerized applications, right? So even though modern containers are super efficient, you can see that almost less than 1% of GPU compute workload overhead that you will get. So that is completely fine if you have very huge workload, and container import may take maybe 10 to 30 seconds for large NGC images. So that is also fine for first import, and basically then it works perfectly fine, right? So when we will talk about these containers and AI workload deployment through containers, we will see in practice from end to end how to use these GPU enabled containers for the AI workload deployment. One thing to remember, always mount datasets as volumes, because it should not be inside the image, right? So this should be mounted as volumes. So this is just one such suggestion which people usually miss while using this containerized application for the AI workload deployment. So in summary, the AI software stack that you have seen, we have different layers: the frameworks, the compilers, the libraries, the runtime, the driver, kernel, as well as the hardware, obviously. And you can have several layers of optimizations possible for your AI workload. So if you want to get most out of the performance, you need to exactly know which layer is doing what, basically, okay? Like your cuDNN provides convolution or attention primitives. Similarly, CUDA streams enable asynchronous data transfer plus the kernel execution overlap, so that your computation graphs reduce the kernel launches. So we usually use CUDA streams for my data transfer as well as kernel launch, okay? Linux performance tuning are also important if you want to deploy very large models in terms of parameter size of GPs of few hundred MBs. So there are several settings that we have talked about, and also we talked about the importance of container toolkit, because it injects the GPU access into these Docker containers, and there are already pre-installed and standard reproducible AI environments that are available from the NGC catalog. So you can go to there and use your own environment that is required for your target. So this will conclude this first week's session. Thank you.